So my name is Markus Jochim. I'm with General Motors Research and Development, and today I'll talk about Automotive Remote Direct Memory Access, or ARDMA, in a software-defined vehicle architecture. So Remote Direct Memory Access has been used in data centers for a while for low latency applications. What we did at General Motors R&D is to develop Automotive Remote Direct Memory Access for use on embedded platforms and for control applications with low latency requirements. On the slide, you see the names of the General Motors ARDMA team. In fact, there are two team members that are not shown on the slide, and those are Bugesh Rikati as well as Zach Steigerwald. So in the upper right corner, you see a simplified SDV architecture with a central compute where you centralize the implementation of both features and control algorithms, with zone modules, or as they're sometimes also called, aggregators, and with sensors and actuators underneath of them. So what is SDV's big promise? In my opinion, the biggest promise is the fact that you're centralizing the implementation of features and control algorithms simplifies updates. So this makes it easier to address issues in the software or to deploy in-market enhancements. Now, on the flip side, what are some of the challenges? If you look at that path that is shown on the slide in red, you will realize that there is a relatively long communication path which results in increased end-to-end latency. So information travels from a sensor through the network to the central compute where the comm stack receives it, where control algorithms are executed, where the comm stack sends out the information, and it traverses the network until it gets to the actuator. So this is quite a lengthy path. And on that path you have different types of latency contributors. There's the network, there's functional software, and then there is the communication stack software. So from an architecture standpoint, there's not much we can do about optimizing functional software because this is use case per use case, so it's specific to the use case. We can absolutely optimize the network, and we can also optimize communication stack software though. So let's have a look at some of the use cases or the type of use cases that we're targeting with ARDMA. This slide here shows three ultra-low latency use cases: steer-by-wire, anti-lock braking, magnetic ride, which is General Motors' active suspension feature. And these use cases can have sub-millisecond end-to-end latency requirements. I'm saying they can have because when it comes to complex use cases, the exact latency requirements always depend on the specifics of the implementation. Now, what we started doing at GM Research and Development is we looked at those latency contributors that I mentioned before, and in the past we have done a lot of work in optimizing the network. But when you look at this example here on the slide, you come to realize that oftentimes the comm stack really makes a significant end-to-end latency contribution. So this is just an example of a measurement that we took in our lab on a traditional comm stack. So this doesn't use ARDMA or RDMA, and you can see what type of hardware we used and the characteristics of the software. And of course, the measurement results always depend on the implementation, a lot of details, but you can see the result at the bottom, and you can find that in this particular case, the measured comm stack TX and RX contribution in this AUTOSAR environment was about 950 microseconds. So that would be essentially all of your 1 millisecond latency budget that you can afford. So how do we address software comm stack related latency? The easy answer is get rid of the software comm stack. Now have a look at the left side of the diagram or the slide where you can see a non-ARDMA system with two ECUs, a sending ECU and a receiving ECU. You can see an application, and you can see the comm stack with UDP, IP, and a driver. and below of that an Ethernet controller. So now in such systems in general, the implementation of the COM stack is highly optimized. It doesn't necessarily follow the pure layering structure of the protocol. It is optimized in order to minimize the number of copy operations, but in general, in those software COM stacks, you will find copy operations and data manipulations. Also, the application runs in user mode and the COM stack runs in kernel mode, which results in context switching related overhead. And then finally, the execution of the COM stack obviously is done by the MCU. So the MCU concerns itself with data shoveling type of tasks, and that results in higher MCU load. Now, on the right-hand side, you see an ARDMA system. I will talk in more detail about how it's going to work, how it's working on subsequent slides. But just the first point here that you will notice when you look at the diagram is that it does not have any traditional COM stack. So there is really no copying of data done in software, so it's true zero copy. Also, there are fewer context switches between user mode and kernel mode, and because essentially all the tasks of data moving data around are done in hardware, there is also a lower MCU utilization. So let's now look at how ARDMA works in some more detail. Before doing so, let's talk about what are the key operations of an ARDMA system. There's two key operations. One is remote write and one is remote read. So remote write enables a sending ECU which has an application that just puts some data into an application data buffer. It enables that node to write that information into an application buffer that resides on the receiving ECU. So a remote read, on the other hand, enables an ECU to read data that is actually located in an application buffer on another ECU into its own application buffer. And then another characteristic or basic principle is that all the data communication and the data communication protocol of ARDMA is done in hardware. It's done really at the lowest layer, ARDMA Ethernet controller hardware. So to bring things more to life, let's walk through a simplified example of an ARDMA remote write. So what you see here is a somewhat more detailed view of a left ECU and a right ECU. And you can see that everything that is shown in blue is software, everything shown in green is hardware. So the applications have some application buffers, B1 and B2, there can be many more of course. And what you see is that buffers can be of different sizes, but corresponding buffers on the left ECU and on the right ECU have the same size. There's an ARDMA library which enables the application to talk to the ARDMA protocol engine. And in the protocol engine you have memory registrations and you have a send queue. Below that there's just the Ethernet controller. So when the system is in configuration still, the first step really that happens is that the application will register its application buffers. So what that means is that it will call these memrec functions shown on the slide, and that will make sure that in this case memory registration number 1 knows the start address as well as the size of application buffer number 1, and you can obviously register many more application buffers. Then what happens next, and this is still while the system is in configuration mode, is that the application on the left side calls a connect init, the application on the right side calls a connect listen, and the sole purpose of this really is to make sure that both protocol engines leave the config state at the same moment in time. So both will transition to RTSR, which is ready to send and receive at approximately the same moment in time. So now we'll assume that the application on the left-hand side will write some data into its application buffer B1 as illustrated by the 5 red ones. It will then create a work request, and the work request W is nothing more than a data structure, and that data structure will contain information such as the type of the work request. Is it a remote read or remote write? Now in our case it's a remote write, and it will also contain the information of which memory registration it is related to. In this case, memory registration number 1, which in turn points to buffer B1. So that write work request W is posted to the send queue of the ARDMA engine on the left side using an ARDMA library function. So what happens now is the ARDMA engine will always process information or work requests from the front of the send queue. So since W was posted to the send queue, the left side ECU will now process that work request. Doing so, the protocol engine will inspect the work request and will see that it is relative to memory registration number 1 and will therefore read the data located in buffer B1 using DMA. Then the protocol engine will run a transfer protocol implemented in hardware that will move the data alongside with an ARDMA header to the ECU on the right side. Since that completes the processing of the work request W on the left-hand side ECU, W will then be removed from the send queue. So on the right side ECU, the transport received B1, or the B1 data, alongside with the header information. It may have taken a couple of frames or just one frame to do that, depending on how large memory buffer B1 is, of course. So what the right-hand ECU will do then is it will extract the memory registration number from the ARDMA header of the message, and that will tell it that this is relative to memory registration 1, which again points to B1, and then the right side ARDMA protocol engine will use DMA to write the data to buffer B1. So of course this was a simplified example. It did not show acknowledgement messages, it didn't show any cybersecurity related operations, nor did it show support for atomic operations. But I wanted to keep this example simple for the purpose of this presentation. One short note about acknowledgement messages. ARDMA has support for optional acknowledgement messages for successful read and write work requests, and acknowledgements are part of the hardware transfer protocol, which means they are very efficient. In contrast, software comp stack implemented acknowledgement messages are usually not efficient. And the main reason for that is that there's multiple handoffs between the communication controller hardware and the comp stack involved for software acknowledgement messages. So let's now talk about the ARDMA specification. Our team wrote the whole ARDMA specification from scratch. The very first version we developed is specification version 0.5. And the sole purpose of that version was to specify and implement the minimum set of functions required to demonstrate latency reductions and MCU load reductions on an embedded platform. So we have two implementations of the ARDMA protocol engine, one in an FPGA and the other in software. The software implemented ARDMA engine, we call it soft ARDMA, can be useful if you imagine an automotive electrical architecture where some ECUs are already equipped with ARDMA capable hardware and other ECUs are equipped just with standard Ethernet controller. In such a situation, you can install a soft ARDMA protocol engine on the nodes that are not ARDMA capable just yet, and nodes can talk to each other. A philosophy that we used right from the start when we developed the specification as well as the implementation was don't copy a word and don't copy a line of code. So everything was developed really from scratch so that we both intellectually and legally own this. Now, ARDMA is a relatively lightweight specification on purpose. The RDMA, the data center RDMA specification has more than 2,000 pages. That is in part because it also specifies the InfiniBand networking components and networking protocol, and in part because of data center related requirements that are not relevant for automotive control applications. So our specification 0.5 has 16 functions on about 60 pages, and we're completely done with v0.5 from an implementation and a specification standpoint. Now, version 1.0 is targeted to address automotive requirements that are not covered by data center RDMA. So what we're doing here is we're addressing those requirements, and we're also exploiting some optimizations that are possible for automotive control use cases that are not applicable to data centers. So some optimizations in ARDMA. We're about 50% done with writing this specification, and we expect it will be about 100 pages, maybe 110 pages total when we're done. Some examples of support that you will find in version 1.0 but not in 0.5 is support for automotive cybersecurity that is relatively close to what is known to as SecOC, Secure Onboard Communication, support for atomic operations, low latency notifications, and for periodic work requests, which are an optimization for periodic control data, which is typical for automotive control. So this picture shows the hardware that we selected for implementing ARDMA. So this is a Xilinx Zynq 7000 with an ARM Cortex A9, and it runs Peta Linux. And let's move now to some latency measurement results. I'll first show here the setup that we used. So we took that piece of hardware that we showed on the previous slide and used UDP IP for comparison. So on that Zynq board on Linux, we run a UDP IP stack and an application on top of it, and then we instantiated an Ethernet controller in the FPGA, and that's our reference system to compare against. Then on the exact same hardware, we eliminated the UDP IP software stack and instead implemented the ARDMA protocol engine in the FPGA. So really what we're comparing is the end-to-end latency from a UDP send on one ECU to a UDP receive on the other ECU, with an ARDMA remote write work request being posted on one ECU and the data write, the remote data write, being finished on the other ECU. So here are the results of our measurements. You see UDP in orange and ARDMA in blue for different payload sizes. For example, for 64-byte messages, UDP's end-to-end latency was about 80 microseconds. ARDMA had less than 8 microseconds. And for 2 kilobytes, which is fairly large for automotive control messages, UDP was in the order of 175 microseconds and ARDMA was in the order of 50 microseconds. So I think this demonstrated a fairly impressive latency reduction. So we did do these comparisons on both systems, the UDP reference system and the ARDMA system, on what you could call clean systems, meaning we did not load up the MCUs with a lot of functional software. So as future work, we will do performance comparisons in the presence of functional load and MCU load, and we'll then also compare the reduction in MCU load utilization in ARDMA versus UDP. So one thing to keep in mind when looking at the latency reductions achieved by the use of ARDMA is the topology that I showed for the software-defined vehicle architecture at the start of the presentation. There's two pieces of the communication path. There is a communication from the sensor to the central compute, and then there is a communication from the central compute to the actuator. So at a minimum, these latency reductions are reaped twice. One other check that we did out of curiosity was a comparison of the latency of data center RDMA versus UDP. So of course this is very different hardware. We used Ubuntu PCs with RDMA capable network interface cards. So this is not an embedded system. So these network interface cards are from Mellanox Technologies and now NVIDIA. And when you look at the data shown here for UDP and RDMA, of course, this is a very different system than the system that we looked at previously for ARDMA. So non-surprisingly, the absolute numbers differ, but interestingly, the relative comparison or latency comparison between RDMA and UDP is similar to the relative comparison between ARDMA and UDP from the previous slide. Now, of course, for ARDMA to be a success, it will ultimately need to be supported by chip vendors that are in the business of automotive Ethernet communication controllers. And since there's always economies of scale at play, a broad adaptation benefits the industry as a whole. So at GM, we do feel that we have a solid specification, a POC hardware implementation, and promising measurement data, and we're determined to move forward with this work. For technology insertion, we see two paths as possible, and these paths are not necessarily mutually exclusive. One path is to collaborate on ARDMA with other industry players, for instance in the Open Alliance or some other standardization organization of industry forum. The second path is a more accelerated path that we can pursue at GM to get ARDMA into our products quickly with a chip vendor that is interested to lead the way together with GM. So if you are an OEM, a Tier 1 or a semiconductor vendor interested in collaborating on ARDMA, then please reach out to me and let's talk. You can send me an email or reach out on LinkedIn. And because our measurement results are only a few weeks old at this point, we are just starting with the technology insertion discussion at this point. We think it would take us the next 3 or 4 months to identify partners and interested industry players and to derive a clear strategy for technology insertion. Thank you very much for your interest in the presentation.